So it is according to my clock. This is 10:15.
Yeah, it's the time. So okay. So the second speaker today is Professor L.A. Esnault from Free University of Berlin. So the title of her talk is recent developments on rigid local system. Please, yes.
Okay, thank you very much for the very kind invitation. And so I don't think there are many among you who are a little bit more arithmetically flavored. So I'm going to go very slowly and to give a little overview. So I start with Simpson. So this is really complex geometry. And in his ICM plenary section address, plenary talk address, he posed the following conjecture. So, which I'm going to explain, but before I have to tell you what is a rigid local system. So if X is smooth, quasi-projective, defined over the field of complex numbers. And if it's not projective, then maybe we fix a good compactification with a normal crossing divisor at infinity. And then we know what is a complex local system. Let's say of rank R. R is the rank, so it's a natural number which is more than 0. And this is the same as a representation of the topological fundamental group into GLR of C, but up to gauge transformation. And then this up to gauge transformation is, of course, a source of many difficulties to parameterize. But in fact, it is very easy to parameterize those objects. One way to think is just like I said, that means you take the representation, and because the topological fundamental group here is finitely generated, then you can write universal equations for a local system by you take generators, so that gives you finitely many matrices, and then the relations, and that gives an affine variety. So it's easy to parameterize all those rows by an affine variety which is defined over Z, and then you can build a GIT quotient. So you have here an affine variety defined over Z, and then there is a GIT quotient here, and the GIT quotient defines what usually is denoted by MBXR, which is a moduli space of rank R local systems. And so it's also an affine variety defined over Z. But we are going to be interested on. We are going to be interested only in points which corresponds to irreducible local systems, which is the same as saying irreducible representation. So let me write 0 here, and then of course it's no longer affine. And so it's a coarse moduli space. So a complex point here corresponds in one-to-one to an irreducible local system of rank R, which I'm going to denote by classical notation, which is bold L. And so, of course, there is another way, which is more geometric, to think of those local systems. You can think of it as being a topological here, fiber space, with the extra properties that the local transition functions are constant. Local transition functions are constant. So once we have this, then the standard definition is that L is rigid. So this is a very important concept we are looking at here. It's rigid if this is an isolated point of the Betty moduli space. Now we can decorate a little bit this notion, and in fact it's better if X is not proper. Then we usually, to have more chance to find rigid local systems, and usually we force the condition at infinity to be imposed. So we fix quasi-unipotent. And why quasi-unipotent? Because in geometry, this is what we have at disposal. Quasi-unipotent conjugacy classes of monodromies at infinity. And then maybe we fix a determinant. Also in the proper case, we fix a determinant, because if the determinant is not fixed, and if even your proper variety has a non-trivial first Betty number, then the local system of rank 1 act on the moduli by twisting, and then of course there are no points which is isolated. So it's better if the first Betty number is not trivial to fix the determinant, and then we fix it as a torsion character. And then you can talk here on the corresponding moduli space. And then you fix the determinant, you fix the monodromies at infinity, and then a rigid point will be also an isolated point here. A rigid local system, once you fix your conditions at infinity, is going to be an isolated point here. And an isolated point, because we are doing geometry, we are doing algebraic geometry, so are schemes of finite type here. An isolated point, so as I said, it's a GID quotient, so it's a coarse moduli space. So a complex point corresponds really to a local system with those conditions at infinity. And yeah, maybe I don't comment more here. And I go immediately to Simpson's conjecture. Simpson's conjecture is that such objects here, L as before, so L rigid, with or without boundary condition. So with boundary conditions, if X is not proper, and without any condition, if X is not proper, then should come from geometry. So at the time he was posing this conjecture, it was really a very daring conjecture. So first I should say what it means that it comes from geometry, i.e. it means that there is a U in X, which is Zariski open dense, together with a projective map here, projective morphism, such that our local system here, which is irreducible by assumption, is a subquotient of the Gauss-Manin local system. So the sum over I of Ri J lower star of C, which by the linear semi-simplicity theorem is equivalent to saying that it is a direct summand. So of course, I mean, it's really inaccessible, and consequently, Simpson already gave a sub conjecture of this conjecture, which is called the integrality conjecture. Which would then follow from the previous conjecture, which I'm going to call geometricity conjecture. Which would say that L rigid implies L integral. And what does that mean, integral? The Gauss-Manin local systems here, which I have written, in fact, are defined over Z. So that means the local system, the big local system comes from a representation in GLR with values in GLR Z, and consequently a subquotient or a summand comes from a representation with values in GLR, of a finite, of a number ring. So this is saying that L is defined over a number ring. Or equivalently, because the topological fundamental group is finitely generated, is equivalent to saying that it's defined over Z bar. That means up to gauge transformation, it comes from a representation of the topological fundamental group with values in GLR Z bar. So that is the integrality conjecture, and one should mention at this moment that this conjecture, which was very daring at the time, in our days, thanks to the work of Petrov, in 2021, which relies on Scholz's method and Liu Zhu, then it comes really from a more general conjecture on which I will say nothing, which is called the relative generalized Fontaine-Mézeur conjecture. So as we see, Simpson's conjecture is a conjecture in complex geometry, while the relative Fontaine-Mézeur conjecture is a conjecture of a number field, for geometry over a number field. And the method of Scholz and Liu Zhu here, that's geometry, p-adic geometry. So it's quite subtle here, and I won't say a single word about this. But I want to mention the following. So remark, in general, if we have any scheme of finite type and a zero and an isolated point, this is the same as a zero-dimensional component. So a rigid L is a zero-dimensional component of the moduli space we are looking at, which is, by the way, I forgot to mention, it's called Betti moduli space, but in another school, it's called character variety of the, and then character variety with conditions at infinity in the non-proper case. So it's a zero-dimensional component. So then there are two cases. Either the zero-dimensional variety component, I apologize, either it is smooth or it's not. And if it's not, I mean, usually another terminology for that is to say that it is a fat point of the moduli. But because we have a coarse moduli space, to say that it's zero-dimensional and smooth, it's equivalent to saying that the Zariski tangent space at the point of the moduli is zero. And because it's a moduli functor, this Zariski tangent space is understood. This is just, so let's say in the proper case, it's a cohomological condition. This is x1 of x of the endomorphism L is zero. That's the Zariski tangent space. So it has to be zero. Or if we fix a determinant that's the trace-free endomorphism of the local system, and if we fix if x is not proper, then we have those conditions at infinity. The Zariski tangent space is also easily computed. It is H1 x bar of the intersection cohomology with values in the endomorphism. But if it is a fat point, then maybe this group here is it means exactly that this group has a dimension which is more than 0. This one or this one, depending on the moduli problem we are looking at. So those are called. So let me write here. Those are called here the smooth points on the moduli. So in that case, if it corresponds to a smooth point, one says that L is cohomologically rigid. And then I don't want to say much more about this, but I want to mention the theorem here from Michael Groschenik and myself in 2018, which is L cohomologically rigid implies L is integral. So it is really a positive answer to Simpson's conjecture under this condition, cohomologically rigid. And there is one thing I didn't say here is, of course, cohomologically rigid. So maybe I should write here in green. Cohomologically rigid implies rigid. Because let me repeat in words once again, rigid means zero-dimensional component of the moduli, and cohomologically rigid means zero-dimensional component plus smooth, no multiplicity. So, of course, I will say a word here, and I will not present the proof. In fact, it's very well documented in the literature now in various different places. But I will say a word here on the light pattern of the proof. And first, before doing this, let me remark here that we have two sources of rigid local systems in the literature. I mean, I should say here two sources, I should say two series. Because there are also isolated examples, but here we have really a series. The first one is everything which is coming from the work of Nick Katz. We assume that the dimension of X is 1. So now Nick Katz proves that if there is an L which is rigid, then necessarily X is P1 minus a certain number of points, finitely many points. And more is true. He classified them. First, he proves that all are cohomologically rigid. The second thing is proves that they are all coming from geometry. And in fact, I can say in words here, essentially, they are coming from this kind of geometry. You take your finitely many points and you take a branch cover of P1 in those finitely many points plus one moving point. So then you take the cohomology of this variety or subquotient. And then as you move this moving point, then you define a local system on P1 minus those finitely many points. And then the rigid local systems are coming from such local systems. So it's really coming from geometry. And this is an explicit geometry. And so this is one family of example. And of course, it answers positively the conjecture of Simpson, but historically it went the other way. That means the conjecture of Simpson, the work of Katz, I apologize, predates the motivicity, the geometricity conjecture of Simpson. So this is one source of example. And another source of example is coming from arithmetic geometry, that's the Shimura varieties. Now, the Shimura varieties are three, essentially of two types. One type is a closed subvarieties of the moduli of abelian varieties, AG, and some quotients of those. Those are called Hodge type and abelian type. And another type is called another type is classified by the ranks. This means rank, real rank is at least 2. In the terminology of the linear, those are the general Shimura varieties. For some other persons, those are the exceptional Shimura varieties. But at any rate, for those, Margulis superrigidity implies that all local systems are rigid. So this is, of course, quite a strong condition, but what we do not know in this case, and in fact, we are very, very far of knowing this. Let me write and then comment. We do not know they are geometric. And if we knew that, then we would have some modular space for those Shimura varieties. Because, for example, for the Shimura varieties of Hodge type, this is a modular space of an abelian scheme together with some conditions, some cycles, Hodge cycles, and so forth. But here, for those exceptional varieties of higher rank, of real higher rank, we have no geometry which enables us to produce a Shimura variety as a modular space of some geometry. And then, so in particular, because all local systems are rigid local systems by Margulis, to understand this geometricity conjecture of Simpson would also probably describe, give a complete, a new insight on those Shimura varieties. Nonetheless, it is a case that they are, of course, because of this superrigidity, they are all integral. So the integrality conjecture in this case is void, because to say that all local system factors through the reductive group, I forgot to say this superrigidity implies that they are rigid, but superrigidity it just means that the local system, in fact, is a representation of the algebraic group, the algebraic reductive group. So it is integral. And yeah, and in addition, they are cohomologically rigid. So again, this example is cohomologically rigid. In fact, more is true. If the Shimura variety is proper, it's cohomologically rigid, and if the Shimura variety is not proper, you remember that the right Zariski moduli space was an intersection cohomology of the local system or of the trace-free local system, depending on the problem we are looking at. And this one is a sub of the H1 on the open, because we are just looking at an H1. And in fact, this group here is 0. So it's really not only cohomologically rigid, fixing the boundary conditions, but in fact, it's cohomologically rigid, even if the modulus problem was posed in such a way that we don't fix anything at infinity. So we can deform also in that direction. So those are two theories. And for years, since we were doing this work with Michael, everybody was asking us whether we had an example of a rigid, irreducible local system, which is not cohomologically rigid. So I will present an example, in fact, a series of examples in any rank soon. But let me show you why it is important, why it was important in the proof with Michael to get to have this cohomological condition. So let me write here, use of the cohomological condition. In the proof with Michael Groschenik. So the proof goes like this. it's a very strange proof, but it's not strange, but somehow you will see exactly where it is important and where, using this method, we cannot bypass this condition. We cannot get rid of this condition. So you, because I was saying that all those local systems accept it's a problem of finite types. There is a modular space to say that we have a zero-dimensional component of this variety implies that the zero-dimensional component is defined over a finite field. So the L, which is rigid, implies that it's defined. That means it corresponds to representation with values in. It's defined over Q bar. And because the fundamental group is a finite type, in fact, it's even defined over number field. Or maybe I call it K because I'm used to call it K here. I apologize. But again, because the fundamental group is a finite type, in fact, it's defined over a number ring where we invert here finitely many primes. So it's defined over O, K, and let me write here 1 over n. That means up to gauge transformation, it corresponds to representation of pi1 x of cx with values in GLR of OKN, 1 over n, I apologize. So the problem is what to do to show that, so the problem is to show that in fact n is 1. And which is equivalent to saying, because the representation is irreducible, is equivalent to saying that the trace function from the fundamental group to, let's say, K bar, Q bar, which assigns, or in fact, it has values in this O, K, 1 over n, which assigns to G the trace of rho of G, in fact, lies in some OL where L over K is finite. It's a finite field extension. So this is equivalent. So the way we proceed is like this. We start with a topological fundamental group. I don't write the best points here, so it's very imprecise. And by the Riemann existence theorem, its pro-finite completion is the same as the étale fundamental group, which I just write like this. I don't write étale here. So now by Grothendieck best change theorem, we can go to any, so X is defined over, let's say S. S is a scheme of finite type over Z. So we can take any p-adic point of X and restrict them. So let me denote by F here a p-adic field, p-adic pointer. So let's say, let me write here. We have a spec, or let me write QP bar simply to S. So it's the same as Q1 QP bar. So now let us take P large, so that we have good reduction. So if we have good reduction, we have Grothendieck specialization homomorphism, which lends into P1 of X over FP bar, which is a mod P reduction of the variety. And if in case X is not proper, here we have to add the temp fundamental group here. I don't discuss this. Let us assume it's projective for simplicity. And then, you know, a representation here, which has values, and now we take L large, which is more than this P, and which is also more than all the N's, which are bad denominators here, possibly bad denominators. Then we can make out of this, so we look at this, we had this representation here, which had valued in GLR of O K 1 over N. So then it factors through the étale fundamental group, which is the same, oops, sorry, which is the same. So there is factorization. So this gives this. And then this representation, when we take L large, we take L, we fix L more than all N. So maybe I should not say that. I apologize. Let me write this. That is not correct. Forget this. Let us take L large here. We had taken P large so that we have good reduction, and we will make it more precise later on. So this representation here, why did I lose my light here? Can you still see something?
We still can see. Yeah.
Okay. Okay, it's fine. So we have this representation here with values in GLR. So it's coming back here. O K 1 over N. So I can take an L which is large enough and a place of OK, which divides L. So I obtain an L-adic representation here. Let's say the L bar. In fact, it lands in some finite extension, which is, let me write OK lambda here. So that's a completion, that's an L-adic field. And then, so it has a residue field, KL, let's say F lambda. And then the kernel here is pro L. I don't write it. So Grothendieck specialization homomorphism is going to tell us that, so we had here this group here. So it factors through this group here. And the kernel here factors through the term fundamental group of the mod P reduction, because Grothendieck specialization is an isomorphism on the pro L completion. So if we take L, which is more than the numbers which appear in the finite residual representation, sorry, if we take P more than the numbers, let's say the cardinality of GLR of F, the finite reduction here, I'm sorry, FQ, excuse me, I'm not focused. Then, and we still have good reduction, then the factor rho will factor through P term in characteristic P. Let me write here T. So this is one thing. And on the other hand, one of the reasons why Simpson posed this conjecture is to realize that rigid implies arithmetic. Let me not argue the way it does. Let me just take it as a black box because I'm running out of time. And arithmetic means that in fact, P rho, the local system which is defined by rho t, descends to the arithmetic fundamental group. So here I had written FP bar, but it descends to this. So we had here GLR of QL bar. So we have this arithmetic local system. And now the proof goes applying the Langlands conjecture in the sense of Laurent Laforgue plus Drinfeld, which enable us to, which enables them to solve Delign's conjecture on the existence of companions. And those companions have the properties that to the local system LT corresponding to rho t, once you fix an isomorphism here for any L prime which is different from P, so for example, L prime dividing N, then there is a new local system, let's say sigma, which is a QL bar local system, and which has the same L function. And because it has the same L function, in particular, it will have the same cohomology. So we had this way here. So we obtain a new local system here. So we can go up all the way back and we obtain a new complex local system. In fact, a new QL bar prime, and I should say topological local systems. This would be more precise. And because this one was not only a QL bar prime local system, it was a ZL bar prime local system, then in fact, we obtain a new topological local system where the prime lambda above L prime is integral. So what we need, and this is what I wanted to say, is to be sure. So we want to be sure that this new topological local system is also rigid. And that we cannot prove. The only thing we can prove is to use the cohomology and to say that this cohomology of the companions, which correspond to this new local system, is the same, the étale cohomology geometric is the same as the cohomology of the L we start with, viewed as a local system on X over FP bar. That is provided by the theory of companions. So by the comparison between Betty and étale cohomology, we can say that H1 is going to be the same for this topological local system we constructed. So if we assume that the H1 is 0, then it's going to be cohomologically rigid if L is cohomologically rigid. This way we establish a bijection between the cohomological rigid local systems with those which have no L poles, and this shows that the system is integral. So that's the end of the proof, and it shows that we cannot bypass this argument here. So now in the remaining times here, I have like 20 minutes. Let me show you a construction which I just performed with Johan de Jong and Michael Groschenik, which is based on an example in algebra, so not geometry, of Lubotsky-Magid. So all the work here is to try to adapt their computation to geometry. So the computation works in any rank. I'm going to give you rank 2. So I will suppose R is 2 because that's the first case we have to consider. So the final theorem is going to be for any R at least 2, they are rigid, non-cohomologically rigid local systems. In fact, the theorem goes on. It's more than this because there will be a second series of examples in the non-proper. So that is for X proper. I mean, for any rank, we are going to construct a projective smooth varieties with a rigid local system, which is not cohomologically rigid. And for R non-proper, we are going to construct an XR, which is non-proper, and an LR, which is rigid and cohomologically rigid in the moduli space I was saying before, where we fix the determinant. That is not important, but we fix the monodromy at infinity, but it's rigid and not cohomologically rigid in the moduli space where we fix nothing or we fix the determinant at infinity. So, I mean, the second example is quite fun, but I won't have any time to tell you how it works. So let me start with construction here. So we have the so-called, I think, canonical or something representation of S3. It acts on Z2. So first it acts on Z3 by permuting the factor, and then it acts on Z2 here, which is a kernel of the trace morphism from Z3 to Z, which assigns to A1, A2, A3, the sum A1 plus A2 plus A3. So it's well known that this representation, let me denote it by lambda 0. So this is a rank 2, it's a representation of S3 in GLR2 Z2. And it's well known that it is absolutely, I apologize, absolutely irreducible. That means it's irreducible viewed as a representation in GL2 of C2, for example. So that defines, because there is such a representation, this defines a group here, which is a semi-direct product of S3 acting on Z2, or if you prefer, you have an exact sequence here. Which I'm going to denote by star here. And then we have this representation here, rho 0 in GL2 of Z2, or of Z, I should say Z, I apologize, which lies, yeah, Z, I apologize, which lies in GL2 of C. So, of course, the ideal would be, I say, of course, I didn't explain. So maybe I don't comment and I just go on with the construction. So that's the first part. The second part is we are going to modify a little bit this construction by doing the following thing. We take an elliptic curve. And then we take the abelian surface, which is the elliptic curve here twice. But then we undo it with the action of S3, which is going to be 1 on the elliptic curve, and the action rho 0, we just explained before here. So if you like, this lattice here, it has basis vectors epsilon 1, which is E1 minus E2, where the I is the canonical basis of these three, and epsilon 2 is E1 minus E3. So that means here, the action, if you prefer, when you have here X, Y, when you send it, for example, the two tau 1, 2, it's going to be minus X and then minus X plus Y, etc. Just to be sure we understand each other. So we have an action. So on the other hand, we do the circumstruction. And the circumstruction is telling us that, I mean, it works like this. We take a smooth projective variety, still over C, with a free S3 action. So then we can form the variety Y, which is A cross P, and then it has over C, of course, and it has a S3 action, which is diagonal, because it acts on A, it acts on P. So we can take the quotient here, X, which is A cross P, which is Y, I apologize, I should say Y here, which is Y defined by S3. And because the action is free here on S3, this is smooth projective. And then we have the Galois theory, which is telling us that the fundamental group of P1, let me write a point here, a base point, which is going to be the image of 0 in the abelian variety and some little p here. So let's say little y and here little x. Then it contains, I mean, it factors through S3 surjectively because of the Galois covert here. And the kernel is P1 of y, which is the same because P is simply connected as P1 of A based in 0. So we have an action like this, and this P1 of A, what is that? It is P1 of E, this three. Z2. So P1 of A first, I should write it is H1 of A. And on the other hand, I claim that here we have the action of S3 on P1 of A, which is H1 of A, is precisely the action which we said before. So we had rho 0. And why that is because this is built into the construction of Serre. This exact sequence here is the same as a homotopy exact sequence. For the fibration, so we have here Y and the quotient X. Here we have the quotient to P. Here we have the quotient to P. So this is Y over S3. So here the fibers are A. And in fact, this fibration has a section here because the point 0A is fixed. So we have a section here which is coming from the section 0A cross P to 0A cross P over S3 because it's a fixed point. And that enables us to say that in fact it's this pi1 of X is a semi-direct product. So let me write like this. And as a representation here, if we write the representation we had before, we had rho 0. It's coming from, I'm sorry here, the action is going to be via the action rho 0 plus rho 0, where the plus here is not canonical. So I apologize, maybe I should put some color here. The plus here, there is no color, I apologize. This plus here is not canonical. It's coming from H1 of the elliptic curve here. But the action of S3 on rho 0 is the one we described before. So now I come to the argument here. So the first lemma is that, so we define, maybe I forgot to give the definition here, I apologize. So the local system, maybe I write it in red here. So the local system L, it's not right, doesn't, which we define is a local system which we define as before. So that's the representation we had before. So which corresponds to rho 0. So the claim is, I forgot to say, it's a representation of S3. You remember you have this exact sequence. So maybe I write 2 star for the exact sequence. So of course, L corresponds to S3 and then precompose by the surjection from the fundamental group to S3. So the claim is that L is rigid. And the second claim is that L is not cohomologically rigid. So let me write by, let's say, claim 1, claim 2. Let me start by claim 2. Claim 2 is, in fact, what Lubotsky-Magid do, because it's an abstract thing. We are looking at H1 on X of the endomorphism L. So that is the same as H1 pi1 of X endomorphism L. But because we are looking at local system with characteristic 0 coefficients, we have the Hochschild spectral sequence. So the Hochschild spectral sequence is going to tell us that this is H1 HA of A endomorphism L, and from this the S3 invariant. Now, endomorphism A, the character table, and this is precisely what Lubotsky Magid compute. The character table of this is yields the information that the endomorphism of A, which is 4-dimensional. This is a trivial representation, the sign representation, and this is L0, or if you like, rho 0, which is our representation. So now H1 of HA, L itself restrict to H1 of A because it's coming from S3 is trivial. Consequently, the H1 here is the same as the Rom over S3 of H1A, which you remember as a representation is rho 0 plus rho 0 with values in C plus sign plus rho 0. So that means it's 2-dimensional. So that's the proof. So this is not a big deal. So the funny thing is a claim 1. So what time is it? Do you still have a, yeah. Claim 1, I claim that L is rigid. So the proof here can be done as follows. So you remember that L here is the exact sequence, here the homotopy exact sequence is here. You remember that L came from a representation of H3. So we assume we have a deformation. So assume we have a T here, which is a deformation of L0 in the character variety. I'm sorry, I had denoted as a modular space. I apologize. MBX2. We have no, by the way, this condition here, remark here, you could also fix the determinant. It will still be the case that the endomorphism 0 here, it's still 2-dimensional because the homomorphism here takes rho 0 to rho 0 and has nothing to do with the determinant which is here. And the same discussion is going to be valid here, but I don't insist. So we have a T here, and we assume that at time 0, it sends T to L. So we look at the complex points here. And now we take LT. So I assume it's connected, of course. So we take LT. So you remember our homotopy exact sequence here. So at time 0, but of course, at time T, I don't know it does. So of course, I restrict to the abelian representation here. So we restrict LT to H1. And we want to show this one is trivial. Because if it's the case, then it is, if it's the case, let me finish the argument. If it is trivial, where is our exact sequence here? If it is trivial, then LT factors through S3. So in fact, the deformation is a deformation of S3 representation of rank 2, but we have only finitely many such, and T is connected, so then it is rigid. End of story. So what we want to show is that the restriction of the representation to H1 is trivial. So, but on the other hand, H1 is normal in pi 1 of XX. So Clifford's theory is going to tell us our representation was irreducible. That's a classical representation. So we know that if we restrict to a normal subgroup, it is semi-simple. And H1 is abelian, so it's a sum of two characters. Let me denote them by KT1 and KT2. So the order is not well defined, of course, but what is well defined is them up to an order. So in fact, those so you can write them KT1, KT2 as a representation of H1 in C star, and then 2, and then modulo S3, this is well defined. Modulo S3, I apologize. But on the other hand, because LT is defined over P1X, then when we restrict it to the sub, which is normal, it is invariant. So it's invariant under the action of S3. And consequently, if I just consider the set xt1, xt2 as a set inside of the characters, then this is invariant under S3. But where S3 acts like it acts on H1 as we learn. But so that means it's a union of orbits. So if it is a union of orbits, so it's a union of orbits. But it has cardinality at most 2. I mean, maybe the 2 are the same, but it's at most 2. So so that means that at any rate, because we have an order 3 element, which is a permutation 1, 2, 3 of S3, it has to stabilize each of those characters here. So T1, 3 of chi tie E is chi TE, chi TI, I apologize. T1, 3 of chi TI is chi TI. Okay. And this you compute easily, and I don't do it now because, but it's trivial. This implies that those points are torsion. In fact, you will see immediately one has order, if I remember correctly. Let me look at my the computation here. I made it precise. One has order 3 and one has order 2. So tie I, 6 tie I is trivial. 6 is the order of S3 here. So they are torsion. But now you have the situation, so you have the situation, even if you look at modulo S3, you have the situation that your points are Q-bar points, but that doesn't exist. You cannot have a connected scheme of dimension at least 1 with the property that the image hits only Q-bar points. So consequently, the image of T, so this defined over Q bar. Consequently, the image of T here is the same as the image of L. I'm sorry, the notation was different. The image of 0, I had defined 0 here. I'm sorry, I should have said T0. This would have been more elegant. So I call it T0 here. I apologize. But the image of T0 is the same as L restricted to H1, which by the very definition was trivial. So we conclude exactly what we wanted. We conclude that LT factors through S3, and that's the end of the story. So in the remaining 2 minutes here, let me write the second series of examples. And you see, this example easily generalizes to S3 replaced by Sn for any n more than 3. And the representation being the canonical representation, that means the kernel of the trace. Or maybe it's called standard representation, I'm not sure. So, of course, each time the variety changes because here we took this elliptic curve and then tensor Z2, and in general, this would be tensor Zn if you look at the symmetry group in n+1 variables. And let me say just one word on the second construction. So I have 2 minutes to give, I'm sorry, it's written, badly written, construction. There is one, you know what is this canonical representation we had before? There is one way to make it geometric in a more direct way as what I said, because what is a way you can represent this canonical or standard representation is by thinking of it as a representation of S3 acting on H0 on P1, and then the one forms with log poles along 0, 1 in infinity. This space has 2 dimensions, so this is C2, and the representation is exactly the representation we did. Now, the fundamental group of P1 minus 3 points, as we know, is really the largest possible we can think of. That's a free group in 2 generators. So this is too big for the construction. So we go to the Jacobian of Serre. So the Jacobian of Serre now is GM of 3 divided by GM. So if you like, it is naturally embedded into P2. And I forgot to say the action here was the action exchanging the 3 points. And now here you have 3 lines, and the action of S3 is exchanging the 3 lines. And this is precisely the construction you do. So the new Y, you do again Serre construction, so you do Serre twice, so to speak, for the Jacobian and for the construction I already explained before, but now I do it in this context here. You pose Y being J cross P, the same P as before, divided by the diagonal, divided later on by the, so it is endowed with the diagonal action of these 3, and you take the quotient here. So it has a natural compactification in, so you have the compactification here in P2 cross P divided by S3. So you have the natural compactification here. And then it is a very amusing computation on the geometry of the situation to show that the group, the intersection cohomology group dies. The reason is, so now I forgot to say, the H1 you have, the H1 on the open of the endomorphism, I call it L here, I don't give details. So H1 here is C. And then all the intersection cohomology now is going to be the kernel of this group in restriction to the monodromies at infinity. And then it's an amusing exercise on the geometry to say that, in fact, when you go to the boundary here, then it's an isomorphism. And consequently, it kills the kernel, and then you kill the non-cohomologically rigid property you had when you look at the boundary condition. So I exceeded by 2 minutes. I apologize. I'm finished, and thank you for your attention.
Thank you. Yeah. Any question from the audience?
So, Ellen, maybe I have a question. So, in the pool for the integrability condition, you use to air-to-air prime company. But my question
I'm sorry,
is,
can you repeat
okay.
I could not.
In the pool
for the
Simpson's conjecture for the integrability condition, you use the air-to-air prime company technique.
Yes.
Can you also use P2L company?
It brings no new information.
Brings no new information.
No, it gives no new information. I apologize. No. What it yields is the following. Is, I mean, in the second article with Michael, so we proved that for P very large in the projective case now, then the p-adic local system have a specific crystalline property, and this enabled us at the same time. I mean, not depending on this, but at the same time, we prove that in that case, for the cohomologically rigid condition, you have a false set of companions. That means not only P2L, but also L2P. So, but to look at the P companions doesn't help anything, because here, the P here you take, here in the argument, is larger than the back primes in N.
Okay. So thank you. So My second question is, can you consider also no rigid local system in the modular space, but as isolated point in the cohomologic locals in the modular space?
The examples we have do not give this. It gives rigid local system, which are rigid whether you have boundary conditions or not. But if you have boundary conditions, then you kill the multiplicity, and if you don't kill the multiplicity. In fact, in the two cases here, I should emphasize the fact that our construction here, which relies on the work of Lubotsky and Magid, yield rigid, non-homologically rigid local system with finite monodromy. We don't have an example with infinite monodromy.
Okay. Thank you.
Yeah. Thank you for the questions.
Any other question?
Professor Esnault?
Yes.
Is your local system motific?
But it's finite monodromy. So
It's finite monodromy. I see. So it's a factor S3. I see.
Pardon me?
Okay. So it's factor S3. So the back construction is.
Yes, that's a construction. So it factors with 3. So the more generally to SN. So, 1 second. I apologize. Hallo? Warte mal, ich kann nur erst später anrufen. Ich rufe dich an. Entschuldigung, ich bin am Zoom. Entschuldige mich. Okay.
Yeah. Okay. Yeah.
So it is integral. It is all this, but it's not homologically rigid.
Yeah. Sorry for the stupid question. It's a by construction.
No. It's not silly at all. I mean, it's a natural question.
Yeah.
Any more questions?
So do we expect rank 1 example exist?
Pardon me, do I expect what?
Rank 1 local system.
No, rank 1 local system, as I said, I mean, the peak number, I mean, the modular space of rank 1 local system is a torus. So you have no isolated point. So to remedy this, I mean, if the first Petit number is 0, then you have only torsion local system. I mean, when I say torus, I exaggerated. It's an extension of a finite group by a torus. So it is never rigid. So unless the first Petit number is 0, then it's just a finite group, then of course it is rigid. And then in order to have more examples to remedy this situation, usually one fixes the determinant as a torsion line bundle. I mean, we need torsion to make our proof work, and also to pose the question of motivicity, because motivic local system will have torsion line torsion determinant bundle, determinant local system, I apologize, and we'll have the condition quasi unipotent monodromy at infinity by the theorem of Briskin and Grothendieck.
I see. Thank you very much.
Is that okay?
Yes.
Does that answer? Yeah.
Yes, perfect. Thank you.
Yeah, thank you for the question.
Any other question? Prof, just wondering, you work with symmetric group S3, or you can also do with SN. So instead of the full symmetric group, if you take a transitive subgroup, does it work? Transitive means there's only one orbit,
Yeah, sure. But I mean, you have to be sure that it works, right? I mean, here, you have several miracles. The first one is that when you take, that's the most important one for the discussion, when you take the endomorphism of L, which is 4-dimensional, okay, then you retrieve the 2-dimensional local system you had. If you didn't have it, then H1 would be 0. And okay, then you would have a smooth, I mean, you would have a homologically rigid local system. So you need already this, and that is true. In fact, I didn't check, to be very honest, but I'm pretty confident that if you do the thing in higher ranks, then this is the same thing. That means when you look at the endomorphism of rho 0, where rho 0 is a standard representation, the kern of the trace of Sn plus 1, so it has rank n, then it will be the case that you retrieve the rho 0 inside of the endomorphism. So then you have what you, so that's the first condition you need. And if you don't have that, and you take only a subgroup of S3, well, you don't have much of a choice, right? So
yeah,
you take
I mean,
a permutation. Oh, Sn, yeah, okay. Then you have, of course, much more. Maybe you can do with the alternate group. I don't know. But here, the most important point in the argument is that the range here is smaller than an orbit, at least one degree of the rank is, just 2 was smaller than 3 here. So in general, you need an element of order, something which is larger than the rank of the local system you are looking at. So here you have several facts which makes the argument work. So I don't know what to do with the sub. Maybe it works, but I haven't thought here.
I see. Thank you. Yeah. So it's quite late. Your thanks to Prof. Esnault for the very nice talk. Yeah.
Okay, thank you very much.
So
And,
maybe
bye-bye, and I wish the best to all of you.
Yeah, sure. So maybe we see again 2 weeks later. Yeah. So we end the session today. So yeah, have a nice your morning, right? Still okay. So we are evening. Yeah.
Okay. Yeah, sure. Thank you very much, and
Okay.
bye-bye to everybody.
Yeah. See you
Thank
again.
you.
Bye. Yeah. Okay. So I guess we leave.